Okay, so the next one that is we are going to cover is the phenol reactions. So there will be several reactions for phenol and we will be covering all of them. So in the reactions of phenol, the first reaction which we are having, that is reaction due to OH, that is because of the acidic nature of this phenol. So the first reaction in this case we are having because of the acidic nature of phenol. So this is a reaction due to OH which is present in this phenol. Okay, so the phenol one which we are having, this is referred as the phenol. So for the phenol we will be having the reaction first one with sodium. So it will be hydrogen exchange, it will become ONA, along with that hydrogen will be released. The next reaction which we are having, that is with NaH. Okay, so in this case again the same product, that is ONA, along with that hydrogen gas will be released. Similarly, the next reaction, that is with NaNH2. In this case again the product is same, that is ONA, that is hydrogen replaced with sodium, along with that ammonia will be released in this case. So this is acid base reaction, this is a strong base, this is also a strong base. Then the next one, that is with reaction of aqueous NaOH. So in case of aqueous NaOH, this phenol, this oxygen, sodium, and along with that hydrogen will be released. In this case hydrogen not, there is hydrogen and there is OH. So hydrogen and OH, that is H2O, will be released in this case. Okay, so these are the reactions related to OH. And the next one that we are having with sodium bicarbonate, that is NaHCO3. Therefore there won't be any reaction because this hydrogen is not even acidic enough to react with NaHCO3. But what if we increase the acidity of this phenol? That means we are attaching the groups in it which are deactivating group, and we know the deactivating group such as NO2 is going to increase the acidity of this phenol, that is this hydrogen is more acidic. So if acidity is increased, therefore this will react with NaHCO3, that is sodium bicarbonate, to yield the product, that is benzene with ONA group attached to it, and along with that water will be removed, with that CO2 also will be removed. So this is the reaction, and this compound in here is referred as the picric acid. So these are the reactions due to this OH group. Okay. The second one, that is due to the Grignard reagent. So the second reaction which we are having, that is Grignard reagent reaction. So Grignard reagent, that is RMgX. Now it will react with phenol. Phenol is what? PHOH. So it is having acidic hydrogen. This acidic hydrogen will combine with this R group, leading to the formation of alkane. Along with that Mg is there, this is X, and OPH will be attached to this one. Okay. Then the next one, that is being referred as acylation reaction. So the acylation reaction. In the acylation reaction we are having this phenol which is PHOH. Along with that we are having the CH3 C double bond O Cl, which is a acid halide. So this is having oxygen lone pair, it will attack on this carbon, this bond will be opened. Therefore it will become PH oxygen hydrogen with a positive charge. This is connected to CO minus, the side chlorine, and then CH3. Therefore the next step, that is in the next step this O minus will come, this chlorine will remove, along with that hydrogen will also be removed. This chlorine is removing because this chlorine is a good leaving group. Therefore it will form PH oxygen with carbon, then double bond O, and then CH3 will be attached to this compound. It is referred as phenyl acetate. So this is formation of phenyl acetate in this particular case. Okay, so in this particular case phenyl acetate is there. Now it can rearrange. So in presence of a reagent which is referred as AlCl3, it can go a rearrangement reaction, that is referred as Fry's rearrangement. Okay, so in the presence of AlCl3, it can go a rearrangement reaction, that is Fry's rearrangement, and it will lead to the product, that is OH. And in the ortho position this acetate group will be attached, or at the para position also this acetate group can be attached. this reaction we have already covered in the phenol preparation. This is the last part, that phenyl acetate converting into the acetate attached at the ortho position or at the para position, and this reaction is being referred as the Fries rearrangement reaction. Okay. Similarly, the next one, that is referred as the benzoylate reaction. So benzoylate, in this case we are again having this pH OH, that is phenol, then benzylate, which is pH C double bond O Cl. Okay, in this case this is having oxygen lone pair, again it will attack, this bond will open, so it will form pH, then OH with a positive charge, carbon with O minus, chlorine is attached and pH group is attached. Obvious thing, O minus will come back, chlorine is a leaving group, so it will leave, along with that hydrogen will also be removed. In this case we will be obtaining the product which is pH C double bond O pH. So that is the final product which is present in here. So this is a benzoylate reaction. Now the next one which we are having, that is referred as the Williamson's ether synthesis. So the fifth reaction, which is Williamson's ether synthesis. Now in this case we are again having this phenol. So this is the phenol. Now this phenol, when reaction with sodium, it is going to form, that is PHONA. Okay, so this is sodium that has replaced the hydrogen one. Okay, so this reaction is due to acidic nature of this phenol. So this replacement of hydrogen by this sodium, this is sodium phenoxide. Now it is reacting with RX group. So if it is reacting with RX, this Na and X will be combined and O will be attached with this R, that is in this case phenyl group with OR. This is a ether. Along with that NaX will be produced. So this is Williamson's ether synthesis. This is a ether formation. Okay. The next reaction which we are having, that is the sixth one, referred as anisole preparation. Okay, so this is anisole preparation reaction. In the anisole preparation reaction, again we are having phenol in a reaction with sodium. So it will form sodium phenoxide. Okay, now this sodium phenoxide in a reaction with CH3I, this is RX group. Similar Williamson synthesis only, same thing, that is leading to NaI ka removal. Along with that, this phenoxide ion will be linked to CH3. This is the formation of ether. So this is a way to prepare this compound which is referred as anisole. Okay. Similarly, we can have one more method to prepare this compound only, that is anisole preparation, but another way which is referred as diazomethylene. So the second way of preparing this compound is by the method, that is by use of diazomethylene compound. Now this is CH2N2. Now in this case we are having this CH2N2. In the CH2N2, its structure is CH2 double bonded with nitrogen, that is double bonded with another nitrogen. This is positive and negative sign. Now in presence of the sunlight, this N2 will leave. So this is a leaving group. It will form CH2, which is carbene. So we have formed a compound which is carbene, and carbene is a neutral electrophile. Okay, that means it has deficiency of the electron. Now this is phenol in presence of this carbene, which is CH2. Carbene has vacant orbital. This is a electrophile, so it has a vacant orbital. Oxygen has lone pair, it will donate its lone pair into the vacant orbital, therefore leading to form, this is oxygen connected to CH2, this is hydrogen. Then this oxygen will have positive charge and this is negative. Now this hydrogen will shift, that is this hydrogen will shift to this carbon which is having negative charge, leading to the formation of anisole, that is pH connected with oxygen and CH3, formation of anisole again, which is a ether. Okay, so this is also the anisole preparation. Okay, So the next reaction, that is the phenol next reaction is with ammonia. The reaction with ammonia. Ammonia, as we know, it is a base, and phenol, as we know, it is a acid. So acid reacting with a base, that is ammonia in this case, in presence of a reagent which is anhydrous zinc chloride. So anhydrous zinc chloride, and at the temperature which is 250 degrees Celsius, it is going to produce aniline, that is benzene connected to NH2, referred as the aniline compound, the formation of aniline by use of this ammonia. Then the next reaction, that is the eighth one, reaction with PCl5. That is in presence of PCl5, how this phenol is reacting. So phenol is PHOH. In presence of PCl5, it will do the reaction, that is this combining with chlorine. Along with that, we will be having POCl3, and then HCl will be removed. So this is a similar reaction with that of the alcohol. Phenol is also aromatic alcohol, so it is similar reaction as that of the another alcohols. Next one, that is reaction that is referred as phthalic anhydride reaction. So we are having this reaction, phthalic anhydride is reacting. So phthalic anhydride is reacting with what? Is reacting with phenol. So phenol is PHOH. Now this is having a hydrogen, then phthalic anhydride, which is this one. So this is referred as the phthalic anhydride. Now this phthalic anhydride in reaction with the phenol. This is the anhydride compound. So anhydride compound, this is oxygen. It will remove this hydrogen, and along with that, this hydrogen will also be removed. In that particular case, if this hydrogen is being removed, it will be water removal. Then it will be producing this compound, which is double bond O oxygen. Then this is phenyl group, that is OH, and with that the another phenyl group, because H2O has been removed in this case, and the whole this group has been attached at this particular position. Okay, in the next step, if we are using OH minus, that is a base. Now in presence of a base, what is going to happen? This oxygen has lone pair, okay, and this lone pair can come back by this way, and it can move in here. Okay, if it comes back, therefore there will be a double bond formation, that this is coming back, therefore this charge will be moved, and O will be referred as with a minus sign. So it will be forming like this is double bond O oxygen. Then in this case, this PHOH group that has been attached in here. Along with that, we are having the another one, which is double bond O. Double bond is coming here, and this oxygen with a minus sign. So this has been generated. This compound is referred as phenolphthalein ion. Now phenolphthalein is used as an indicator, and this is a phenolphthalein ion. So this is phenolphthalein ion that has been formed, which color is having pink. Okay, and this is a reversible reaction. If we add acid to this phenolphthalein ion, it will be converted into a phenolphthalein, which is a colorless in here. So this is the reaction, that is phenolphthalein having this reaction, and this phenolphthalein is used as an indicator. Why? Because it changes color in presence of a acid or a base, that is H plus or OH minus. Okay, now the next one, this was the reaction number 9. So moving on to the next reaction. Next reaction is because of this benzene diazonium chloride salt. So the phenol action with benzene diazonium chloride salt. Now this is benzene diazonium chloride, which is pH connected with N2 plus and Cl minus. Along with that, we are having this phenol. Okay, so it is leading to the formation of a dye, which is referred as a azo dye test of phenol. So it is form OH, then this is N double bonded with nitrogen, and this side we are having phenol. It is the formation of azo dye, and this azo dye has a color which is red orange color, which is also referred as a test of phenol. Now let's look into the mechanism. In the next page we will be doing its mechanism. So in its mechanism part, we are having this phenol hydrogen we can remove, so it will be referred as phenoxide ion. So in the phenoxide ion, and then we are having this particular benzene diazonium chloride. So in this case we are having this as N2 plus Cl minus. Wait one second. This is benzene with N2 plus and then Cl minus. Now this is O minus coming back. This will come back, and from the para position it is going to attack on this N2 plus. Now after this attack, what will happen? This O minus is coming back to double bond O, therefore it is double bond, then bonded with nitrogen. Okay, and after this bonding with this nitrogen, it will forming this benzene will be there. And now this will undergo a tautomerization. This is hydrogen, this will come back, this will come back, this will there. So after this tautomerization, it will be forming a azo dye compound. So this is a azo dye, therefore it is referred as a azo dye test of phenol, because it gives a color which is red orange, which can easily be identified by the naked eyes. Therefore it is referred as a phenol test. Next is reaction number 11. Reaction 11th is with beta naphthol. So reaction of phenol with beta naphthol. This is beta naphthol reaction. In this beta naphthol hota kya? So this is referred as this beta naphthol. Two benzene ring connected with OH. It is a beta naphthol. Now this beta naphthol. This beta naphthol is having the reaction that is in presence of a basic medium, that is OH minus. In presence of a basic medium, we can refer it like this one also. So in presence of basic medium, this hydrogen will be removed. This oxygen will be having minus charge. So this hydrogen will go with this OH minus. This minus will come back. This minus will come back. Therefore, this double bond will be rotating. This is the double bond. And in a reaction with this azo dye, this is in reaction with this benzene diazonium chloride, this minus will be coming, and therefore it will be attacking on this N2 plus. So this is reaction. In this case we are having this double bond. This is double bond with O. Then this is nitrogen, that is N2, N double bond N, connected with the benzene 1. So this is the reaction. Now in the next step, again this is hydrogen, it will undergo tautomerization, and after tautomerization it will be forming azo dye. So this is a azo dye reaction for this beta naphthol. This the final product. This is, we are having this OH group, this is N double bonded with nitrogen, and through that this pH group has been attached. So this is the pH. This is also azo dye. Okay, so this has been formed. So this is reaction of beta naphthol with benzene diazonium chloride. Next one, that is 12th. 12th is referred as the Riemann-Tiemann reaction. So Riemann-Tiemann reaction, we have already covered this reaction in the chapter which is chloroform. So this reaction is already completed. I am just going to write that reactions. We are having this phenol in a reaction with chloroform, that is CHCl3, in presence of a base which is OH minus, and at a temperature which is referred as 65 degrees Celsius, we are going to produce silysaldehyde, which is in this case phenol and then CHO group, referred as silysaldehyde. So this is the compound which we have obtained in here. Okay, so this is already we have covered this mechanism. I am not going to write that part again. Okay, so next one, that is the reaction number 13th. So 13th reaction which we are having is referred as Kolbe-Schmidt reaction. Now let's do this reaction. In this case we are having this phenol. These are the name reactions. Rimmer-Timmer reaction, Kolbe-Schmidt reaction, these are referred as the name reaction. So OH minus in presence of CO2, it is going to form a acid which is referred as salicylic acid. Okay. Now we will do its mechanism, that how this reaction is going to take place. So in the mechanism 1 we are having, that is, this is phenol. Phenol in presence of OH minus, this hydrogen will be removed. The acidic hydrogen is removed, therefore we will be remaining with O minus. That is phenoxide ion. Now in this phenoxide ion, now we are having this CO2, that is C double bond O double bond O. So this minus will come back, and from this position this will be attacking. Okay, so this is a ortho attack. It can also be a para attack. So ortho or para, both product can be made. So we can do a para attack also, that is from this position, that is C double bond O double bond O. If this rotates, then from this position also it can be the attack. Now it can be either ortho attack or it can be a para attack. So let's do first for the ortho one. So we are having C double bond O, O minus, this bond is opening and therefore there is a hydrogen. Now this hydrogen can undergo tautomerization. So if it undergoes tautomerization, we will be having this aromatic phenol one. Along with that, this group is present. Now we are having the water. Now in presence of water, water will donate its proton to this ion. Therefore it will be forming a acid which is referred as salicylic acid, and it is from the ortho position. Now this can be done from the para position as well. So the similar reaction that will be done. So this is hydrogen double bond O, O minus, and this one double bond O. Again tautomerization will take place. After this tautomerization, again this is aromatic and this is C double bond O, O minus. Now again in presence of this water, water will donate its H plus, therefore it will be a COH group. Again it is a salicylic acid, but this side there is para position attack. This is referred as Kolbe-Schmidt reaction. In this case, salicylic acid has been obtained. Okay. Similarly, let's move to the next reaction, that is also a named reaction. So the 14th one which we are having, that is referred as Gattermann's aldehyde synthesis. So this is Gattermann aldehyde synthesis reaction. Now in this case we are having this phenol. So this phenol in a reaction with HCN or HCl, along with that we are having AlCl3. It is going to form a aldehyde which is OH, and ortho position CHO group is present, and which is what, which is a salicylaldehyde. So we will be synthesizing this one and we will be having the mechanism. So in the mechanism we are having HCN in presence with HCl. So there is these two groups. Now there is the nitrogen which is having lone pair, so it will attack on this H plus, therefore it will forming HC triple bond N, and then with that hydrogen is being attached. This is having the positive charge. Now we are having the Cl minus. So this Cl minus will come back and this will attack on this particular carbon. So this triple bond will be opened. It will become hydrogen, carbon, chlorine double bonded with NH. Okay, now we are having AlCl3 as well. So Al3Cl3 is a electron deficient species. Therefore this chlorine will go in this aluminium, therefore it will become hydrogen, carbon, then double bond with NH and with a positive charge, because this chlorine is leaving with a minus charge, carbon will remain with a positive charge. Now this nitrogen has lone pair, This lone pair will again come back, and therefore it will be forming Hc triple bond N with hydrogen and then a positive charge on itself. So this is the species which we are having. Now come to the reaction part. Now we are having this phenol. This phenol in presence of a base, that is, this is OH minus, it will be forming a phenoxide ion. Now the reaction in between this phenoxide ion and this Hc triple bond NH which we have obtained. So we are having this phenoxide ion. Okay, this is O minus. Now in reaction with Hc triple bond NH with a positive charge, it can be again a ortho attack or at a para attack. So we will be doing both. Now if it attacks from the ortho position, it is going to attack on the carbon 1. So it will be attacking on this carbon, again this bond will open. So this is a ortho position attack. Now in this case we will be having double bond, this is double bond O. Now we are having at this particular position there is carbon double bonded with NH and then hydrogen is attached to it. Now we are having hydrogen. Again tautomerization will take place, and in presence of H2O it will become a compound, that is double bond O. So if there is tautomerization is done, let's do it in the next step. So this is tautomerization. We are having this phenol which is attached to CH double bond NH. Now the CH double bond NH group in presence of water will hydrolyze, and this NH will combine with this hydrogen, it will be removed, and at this position a double bond with oxygen will be obtained. That is final step, formation of salicylaldehyde in this case. Along with that ammonia is going to be removed. Now this was at the ortho position. The same attack can go with the para, that is another one. This is O minus, it can be moving, and from this para position it can attack on this carbon which is present in this one. So this is attack, this is open. Now again the same steps, that is this one, this is hydrogen, this is CH with bonding with double bond NH. Now this is double bond O, tautomerization, so this aromatic phenol will be obtained again. Now this is CH double bond NH, and whenever it is hydrolyzed, that is water is present, the ammonia will be removed from this double bond N connected with CH. Therefore CHO along with that OH and removal of ammonia is going to take place. So this is the reaction mechanism for Gattermann's aldehyde synthesis. It is referred as aldehyde synthesis because the final product which we have obtained is a aldehyde. Therefore it is referred as a Gattermann's aldehyde synthesis, and the final compound is salicylaldehyde. Now moving to the next one, that is 15th. In the 15th reaction we are having a simple reduction reaction. The reduction, we are going to do reduction of phenol, that is we are having this phenol which is OH. We are putting zinc dust to it. In presence of this zinc dust it will directly form benzene, along with that ZNO will be obtained, or it can also be done with another way, that is in presence of nickel, hydrogen, and the temperature is 300 degree Celsius. Now in this case we will be obtaining a product which is cyclohexane connected with the OH group, that is all the aromatic double bonds, this was all double bond, they have been saturated, all the double bond has been removed and a cyclohexane has been obtained. Okay, so this is the compound. Okay. Then the next one, that is 16th, that is a simple oxidation reaction. In the oxidation one we are going to use a peroxide type of bond. So peroxy bond will be present. So this is phenol, this is hydrogen, and then in presence of a peroxide bond, that is K2S2O8, and in presence of base. What is this K2S2O8? This K2S2O8 has a structure which is OH, S double bond O, oxygen, peroxide bond, then again double bond O and OH. So this is referred as this K2S2OH, which is known as peroxy disulfuric acid, and it is a oxidizing agent. It is a source of oxygen. It is oxidizing agent. There is double bond, there is peroxy bond, and therefore it is going to oxidize this phenol into quinol. So this is OH and this is OH, which is referred as a compound which is known as quinol. So this is the oxidation with the help of a peroxy bond which is present in a peroxy disulfuric acid, or it can also, this similar reaction can also happen in presence of a peroxy monosulfonic acid, that is HCl double bond or OH. Okay, so this is also peroxy bond. This is referred as peroxy monosulfuric acid. Okay. And the next one, that is 17th, referred as a simple bromination reaction. So the 17th one, that is bromination reaction. In the bromination one, we will be having two things, that is with a non-polar solvent and with a polar solvent. This is OH. Now OH is actually a activator. Oxygen is a lone pair. Oxygen has lone pair. It will donate a lone pair into the ring. That means this ring has been activated. Now in presence of a non-polar solvent like that of CS2, there will be monobromination. That is, bromine will be attached either at the ortho position or at the para position. So this is OH, bromine at ortho, and then this is OH, which is bromine at the para. So this is mono substitution of bromine, that is mono bromination has been taken place in this case. Now the same, that is bromine, but in presence of water, and this water is basically a polar solvent. It is going to form, that is ortho and para position will be brominated, but at once only. So tribromo has been connected. So this is referred as tribromination. So must remember this reaction, water, that is bromination in presence of a non-polar and a polar solvent, and this is a very highly reactive reaction. Therefore, in order to control this one, the temperature range which is provided is 0 to 5 degree Celsius. So this is a high rate of reaction is very high. Mention this one, that is rate of reaction is very high. Therefore, to control that, so to control the rate temperature is reduced to 0 to 5 degree Celsius. Okay, so this is the bromination one. Okay, there is a strong, in this case we are having that is OH. This is activator, and this is activating at bromine ortho and the para position. Okay, so this is a bromination reaction. Similarly, we can have a nitration reaction also. So the 18th one which we are having, nitration, that is phenol is there, on phenol we are adding this nitric acid which is HNO3. Now again two cases, that is dilute and concentrated. So dilute HNO3, that is nitration will be done at only one position. Okay, so either ortho or the para in presence of this dilute one. But if it is a concentrated HNO3, again the nitration will be done but at ortho and para position simultaneously, that is trinitration, that is OH, NO2, then NO2 and then NO2, that is picric acid has been generated. This is referred as picric acid, which is a highly acidic compound. Similarly, after nitration, the next one, that is 19th reaction of phenol, that is referred as sulfonation reaction. So in the sulfonation one, again we are having this phenol in presence of sulfuric acid, which is S2SO4, and therefore we will be obtaining ortho substituted product and the para substituted product. So these are the reactions of phenol. So in total for the phenol we have 19 reactions. Okay, so we have completed the reactions for the phenol one.